Hello friends, welcome to the online lecture series of St. Andrews Institute of Technology and Management Gurugram. Myself Satyendra Vats, Assistant Professor in ETCE department. Our today's topic is quantization. Quantization is a process which is used in pulse code modulation to minimize the number of samples in a pulse amplitude modulated wave to a finite number of levels which can be represented using binary digit. It is a part of unit 4th in communication systems. So we need to represent infinite value of analog signal to the finite set of levels in order to convert our discrete signal into digital signal. So first of all, we convert our digital signal into discrete form using the sampling process, and then from the discrete to the digital using quantization. There is a difference between the discrete and digital signal. Discrete signal has the amplitude, continuous amplitude, but the discrete time, whereas in digital signals the time is discrete as well as the amplitude is also discrete. Okay, so we need to represent infinite values of analog signals because the analog signals can have infinite values of the amplitude. So we need to convert that to the finite set of levels in order to convert our discrete signal into binary forms. So representing values of analog samples by a finite set of levels is called quantization. We have already seen the basics in the last lecture. We can have finite set of levels which we can represent using binary digits. So sampling results in a series of pulses of varying amplitude values ranging between two limits. So let's say this is our amplitude signal and we have sampled it using the flat top sampling. Okay, so this is the sampling process we have applied and generated the flat top sampled. As you can see, this is the maximum value of the amplitude and this is the minimum value of the amplitude. So between these maximum and the minimum value we can have a finite number of quantization level. Okay, so let's say we need to convert our sampled signal into L levels or L zones quantization level. Okay, so this is achieved by dividing the distance between minimum and maximum value, that is this value, maximum value and minimum value, into L zones, each of height or size delta. Delta is the, we can say, the step size, and it can be calculated using the maximum value of the amplitude minus minimum value and divided by the number of levels we want to convert our samples into. So if we need L levels, then we would get the step size as delta is equal to maximum value minus minimum divided by L, and the midpoint of each level or each zone is assigned a value from 0 to L minus 1. Like if we have 8 levels, then the midpoint of each zone is assigned a value of 0 to L minus 1, that is 0 to 8 minus 1, 7. Okay, so the resulting L values lie in the limit of signal variations. So these L levels would lie between the maximum and minimum value of the signal. So L values lie in the limit of signal variation with equal amplitude. So all these L values will have equal amplitude or step size. Each sample falling in a zone is then approximated to the value of the midpoints. Like we say that if we have this signal which is lying between 0 and the this value. So this signal will be assigned the half value, that is the midpoint of this range. And like this signal is there, it ranges between 0 to and this value, so it will be assigned 0 to half value. If it is 3, then it will be assigned 1.5. If it is 2, it will be assigned 1. Okay, like in this example we can say that this is the analog signal, then these are the sampled values, flat top sampled values, sample signal. Then we would divide this whole range, that is from maximum to minimum, into L levels. If I need 8 levels, I would divide the whole range into 8 levels. If I need more, that is I need 16, then I would divide it into 16 levels. Okay, this is how we can divide the whole range. And the delta is the, that is the step size, is the difference between two levels, and it would be constant. That is, for every difference between every level would be constant, and its value would be maximum minus minimum divided by the number of level. So let's see an example. Assume we have a voltage signal which has a variation between minus 3 volt to 5 volt, that is the maximum value is 5 volt and minimum value is minus 3 volt. And if I want to use L quantization level, or 3 number of bits to represent our level, I can get the step size as zone width, or the step size as delta is equal to 5 minus minus 3, as 5 is the maximum value and minus 3 is the minimum, and divided by 8. So it comes out to be 1. So delta or step size or zone width would come out to be 1. Okay, so 8 zones would be there between minus 3, because the minimum value is minus 3 and maximum is 5. So there would be 8 zones or 8 levels between this range. So these zones can be minus 3 to minus 2, minus 2 to minus 1, minus 1 to 0, 0 to 1, and so on till plus 4 to plus 5. So these are the 8 zones we can have for 8 levels, and midpoint of each zone will be, for this we would have midpoint 2.5, that is minus 2.5, and similarly for the other levels as well, like 4 to 5 we would be having a value of 4.5. So this is how we can convert our levels to the midpoint values. Okay, now next thing to do is the assigning codes or the binary digit to our quantization levels or zones. So each zone is then assigned a binary code which depends on the number of bits depend on the level. So the number of bits required to encode the zones are the number of bits per sample is obtained as follows. Number of bits required to represent a zone or level, or the number of bits per sample, can be given as n is equal to log base 2 L. L is the number of level. If L is equal to 8, then n is 3. If L is 4, n is of L is 16, n is 4. So this is how we can get the number of bits required to represent our quantization levels. So the 8 zones codes can be assigned then. If we have 8 zones, that is 0, 1, 2, 3, 4, 5, 6, 7. So you all know how we can represent 0 using 3 bits. It would be 0, 0, 0. 1 would be 0, 0, 1. Then 0, 1, 0, and so on, 1, 1, 1. So this is how we can represent our levels using 3 bits if number of level is 8. Okay, so 0, 0 we can assign any level, any combination. Like in this we have given 000 to minus 3 to minus 2, then 000 or 001 to minus 2 to minus 1, and so on. Okay, so now we have two types of quantizers. depending upon the size of step. Okay, there can be two types of quantizer, that is uniform quantizer and non-uniform quantizers. So in uniform quantizer, the step size delta would remain constant throughout the range, but in non-uniform quantizer we can have variable step size. Okay, so first, because uniform quantizer is the main or the important one, we are uh, discussing uniform quantizers. Okay, so in this, if the step size remains same, if if the step size remains same for the whole conversion, that is from minus value or minimum value to the maximum value, we are dividing our system into n levels, then throughout the conversion the step size would remain same, so then it is a uniform quantizers. So uniform quantizers can be of two types: mid-thread quantizer and mid-riser quantizers. They both differ in the staircase representation of the sampled signal. Like if we take this case in mid-thread quantizer, the zero, that is the zero value, would come between the top of a staircase, that is it would come between the top of a stair of this function. So in this, if the x-axis represents the input sampled value, that is x of NTS sampled levels, and the output is the quantizer output. So we can draw the graph as this one for mid-thread quantizer, that is if the input value is minus delta by 2 delta by 2, then the quantizer output would be 0. Okay, the quantizer output would be 0 if the range of input is minus delta by 2 delta by 2. Similarly, if the range is delta by 2 to 3 delta by 2, then the value of our quantized signal would be delta. Okay, so if we have odd number of levels, then we would have a mid-thread quantizer. If we have odd number of levels, then we would have a mid-thread quantizer. And what is quantization error? Is the difference between the sampled value and the quantized value. This difference is the quantization error. Okay, and its value ranges from 0 to del by 2, where del is the step size. So the maximum quantization error possible in mid-thread quantizer is delta by 2, which we can draw using this. So it ranges from minus delta by 2 to delta by 2, like this. Okay, so this quantization error is nothing but the difference between the sampled value and the quantized value we have assigned to that level or the sample. Similarly, we can have a mid-riser quantizer, that is the zero level would come when we go from one stair to other stair. So 0 would come in between this. Okay, so this situation comes when we have the number of levels as even. If we have even number of level, then the 0 would comes in between when we go from one stair to other. Okay, so in this case, if x-axis represent the sampled input and y-axis represent the quantizer output. So for the sampled value 0 to delta, that is this one, 0 to delta, our quantized value would be delta by 2. And if it is from minus delta to 0, then the value would be minus delta by 2. So this is how we can draw the quantized output in respect of the sampled input. In this case, the maximum error would remain the same, that is delta by 2. So we can use any of these quantizers it would make no difference, and the probability of error would be same in both. Again we can draw the error graph as this. So in mid trade type, the origin lies in the middle of a thread, that is on the top of the staircase. The quantizations level are odd in numbers, so if the number of levels are odd, then we will get a mid thread type graph, and 0 would fall between the top of a stair. And if the number of levels are even, then we would get a mid-rise type of function in which the origin lies in the middle of the raising part of a staircase. That is, if we go from one stair to other, then the origin falls in between that. So this is all about quantization, how we can convert a discrete signal into the digital or the binary form, or the zeros and one, in pulse code modulation. Thank you very much.